How much time I have? 30 minutes?
45 minutes.
45. I think for okay. We'll start. Yeah, just start. 15 minutes. Just start. Oh, okay. I can start.
Yeah, okay. So let us start last talk, today's session. The last speaker today is Professor Anatol Kirillov. He will talk on quadratic algebras, elliptic case. So please start.
Yes, thank you very much for the invitation to give a talk. And I apologize for my handwriting because because I thought I have 30 minutes. I just keep very important things. Motivation. My motivation really comes from two things. One thing is Schubert calculus, which I like very much, and another motivation from basically from beta ansatz, which I study from physics, and motivation from Schubert calculus probably well known and
I put this in the...
okay. Well, Schubert calculus very well known, and my point, I try to study Schubert calculus. My point, final point, to find little rotations on rules for Schubert varieties, Schubert polynomials, structural constants for intersection of Schubert classes. In some sense, the answer is ready, but not full. Anyway, this is another consider similar questions for Quadratic polynomials and for what I call the Kirstenbruch polynomials. Because in fact, there are some additional nice cohomology theory which I call Kirstenbruch, which corresponds to the so-called Kirstenbruch formula groups. But I'm not sure that I can anyway. And another very important for me motivation of this work, it is the famous theorem from representation theory. It is theorem of Charles Duncan and later by Eric Ogden and Charles Duncan. It is concerned with the co-invariant algebra of complex reflection group. The Duncan and Ogden prove theorem that for any complex reflection group, finite complex reflection group, one can construct a family of elements called truncated Duncan elements, such that we generate co-invariant algebra for this complex reflection group. And it is well known that in the case of crystallographic case, the co-invariant algebra coincides with the cohomology ring of corresponding Flock variety, because it is still unknown what is analog Flock varieties for exceptional complex reflection groups. Yes, and this is interesting because the truncated Dunkel element have additional set of information, because it is not just element, but it is certain operator, and you can formalize these operators. And in fact, this operators is a formalization of very famous operators, the Demadieu-Lustig operators, or Lascaux-Schutzenberger operators, but it uses some set of relations between these operators which guarantee commutativity of certain operators, and does not use some additional properties, because, as I know, it is still unknown what is algebra generated by the Demadieu-Lustig operators, how to describe relations between these. Okay, and it is interesting to understand why Dunkel operators, what is Dunkel elements, Dunkel operators. In the simplest case, quadrilateral case, it is, has a leading height, which is not right. Sorry, I want to write. We have very simple things. Xi plus sum of u ij, j not equal to I could. This is some maybe bad notation, but I traditionally write is theta I, but that is not elliptic function yet. Okay, so and this xi can be interpreted in many cases. So xi may be operated by multiplication, and this operator acts on the Rietkopf polynomials. Yes, and these operators can be interpreted many ways. For example, with operators multiplication by xi, or as differential operators with respect to variables xi, or shift operators, and so on. There are many interpretations of this element, and I here from 1 to n. So the natural question the truncated Dunkel operators, Dunkel element is element when xi is what I call the equivalent parameter, and later it will be made clear why I call it equivalent parameters, so that it is not a differentiation. But it will be clear from definition of my algebra where the differential part and xi, it is so-called generated Heisenberg algebra. I call it Heisenberg Dunkel algebra, and it is, in this case, this is just recover the algebra of type A. And if you add here shift operators, then you recover what is called toroidal algebra, but it is out of my talks today. I will concern the generalization. One of purposes of my not talk about my research is generalization of Dunkel theorem for equivalent Dunkel elements. I call these operators equivalent Dunkel operators or elements. Yes. Now, yes, natural questions. If now I consider this element as elements, or so I consider quadratic matrix Aij, 1 not sigma I, j not sigma n, and I write I have generators which I can consider free associative algebra generated by this bunch of elements, and these elements have two sense. Later I denote the diagonal element like xi, because they play distinguished role, and element uij when I not equal to j, I call the fields. Maybe it is not correct, it is not particles, but it is fields in some sense. Because these elements really, if you add its differential part, it is curvature of certain vector bundles of what variety. It is curvature, and it is flat. And flat will be clear. It is natural to write what it means flat. Yes, and this is just what I wrote here. Again, I maybe save time. I consider non-equivariant case because okay, maybe okay. But I concentrate myself for elliptic case a bit later, but I want to draw attention to this algebra, because this algebra appears in many cases, in many theories, in geometry, but I have, of course, so first of all, I try to algebra, and then I will try to explain how this algebra related with geometry. How is this algebra related with the Schubert calculus, Quadratic calculus, and the elliptic calculus, and so on. Okay, so what is the relation? Naturally, theta I and theta j is equal, should commute. And this is what I call additive Dankel elements, because there are extension for multiplicative Dankel elements a bit later. So I want that they commute. Okay, probably I leave it as for exercise and give answer. It is easy to write, just put like definition of Dankel elements and write it as a sum of A and B commutators. And first important property of this algebra, again, which is motivated by physics, that this algebra is a local R. First important restriction that this algebra local, and this is important assumption in physics. That means that Uij is Uij and Ujk commute if indices set of indices have a zero intersection. And it is, its definition includes II and xi as well. That means xi commute if Uij if it is all different indices. Okay, I got the exercise to write what does it mean on the commutators. And it means that that this set of relations can be divided on the set which include only elements which corresponds to some algebra of rank 2. Where subalgebra? Because I have in mind general case, it is easy to understand that Ij corresponds to parameterization of positive and negative roots of the root system of type A. And of course, explicit formulas for Dunkel elements exist for any root systems. You can imagine that similar relations but may be involved, but valid for any root systems, for example, for A, B, C, D, E, and so on, and important things for complex Yes, and bad things with my approach that it is very difficult for exceptional cases when you have just algebra given something. Yes, and nice case when you have series, because you can apply inductive argument and prove something. For example, for E8, too many relations and too many generators, and very difficult to prove analog of Dunkel's theorem using definition of relations between these generators. This is locality. This is very important. Another very important, again, from physics, I call it factorizability. That means that, okay, it is easy to write, but these equations for given I, J, and K equivalent to the so-called classical dynamical Young-Baxter equation. Yes, and factorizability means that I assume that it is classical dynamical Young-Baxter equations really is sum of two what is called associative Young-Baxter equation. Okay, and for simplicity I skip anyway, okay. So what is that factorizability? It means that element I already not mentioned that as I mentioned it is Uij in some special case. This was considered by Arnold. This is one of the main of the source of my research. Arnold, many years ago, computed cohomology ring of so-called purebred group. And later it became the theory of arrangement and the description of a homology of complement of relations, or hyperplanes. Sorry. Yeah. And Arnold proved some rather surprising relations. So this is the second set of relations. This is associative Young-Baxter equations for any triple of elements alpha, beta, gamma, alpha plus beta, certain relations. And again I will write, because I consider type A, this is means Uij, Ujk is equal to Uij, okay, Ujk, Uik minus Uik, Ujk. That means because it is okay. Because I think it is visible or not. Because I consider a bit later I will consider unitary case, it is physical case, but for many applications to knot theory and so on, you need to consider full algebra. And very important point is that I treat these relations, okay, this is a relations, and I have a compatible associated another relations that just change the places. This is letters U, J, K. I think it is eta. U, I, K, U, I, J is equal to U, I, K, U, J, K minus U, J, I, U, I, K. It is easy to understand that if you subtract one from another, you obtain exactly the non-unitary form of classical Young-Baxter equation and some tail which corresponds to the dynamical variables commutation over xi and uijk. So this is the, yes, this is basically, and I also write relation between u, xi. For cosmological case, it is enough, you don't need use the dynamic variable equivariant parameter xi. It's okay. Yes. This is the relations, and I think I will write relations maybe on this one. I think this restriction not very important. I like another of Elliptic relations for affine Heckel algebras, degenerate affine Heckel algebras. This is look like uij xj minus, again this is a non-unitary case, uji xj is equal to 1, but in some sense is equal to 1, it is okay, 1, in some cases it may be 0. Or, okay, not 0, but any constant d. D, it is element which commute with all things you want. And this is the further relations. I tell this relation, I consider this relation as a background. Background for any case, this is fixed. This relation is fixed, and basic condition in this theory, which really distinguish cosmology theory and many other things, it is element of uij square. Now, very special element, squares of these generators. It is, I don't see, maybe more, yes, squares generators. This is very important from the point of view to construct integral element. And I want to say, here I don't consider the differential part, that means I consider only truncated Dunkel elements, and I call it quasi-integrable systems by the following reason. The main problem, which one of the problems which I want to consider, I consider relations between Dunkel elements. What kind of relation follows from this set of relations? And it's called quasi-integrable if there exists this elementary symmetric function from Dunkel elements does not depend on uij. That means that there are integral of motion for connections. why this element uij square important? Because first of all, very important things here. First of all, they shows that quantum, Young-Baxter equation in this equation should be replaced by default Young-Baxter equation. That means Lij minus something is equal to some involves I have to write uij square. I consider the so-called Hickey type relation. That means uij square is equal to beta uij, beta some parameter, it is a parameter of quadratic polynomials, plus some what I call the quasi-constant, some psi ij plus qij. What means quasi-constant? That means that qij is central element and it is a correction of quantum corrections. And big problem for me, for not only for in the problem, advance of this theory, but quantum correction, in classical case of phenomenology, it has where number is equal to rank, your Lie algebra is equal to n-1 here. But in some sense, I want to stress that this theory just suggests that real number of quantum corrections is equal to dimension of cotangent bundle. Because relation between Dunkel elements contains this parameter. And this, you have parameters equal Q only for element of corresponding to simple groups, and all over zero, it is just, as I tried to explain, it is just a homology of law parameter. And another thing, why uij separate cohomology theory, and it is a very simple argument, because important things, what is later I consider, I also want to consider element hij, I call the x, uij, x, hij is equal to 1, plus some x uij. And let us consider what is the product x. What is product hij x, hij y? It is easy to see that we say 1 plus x plus y, x plus y. This is not an equivalent parameter. It's just explanation how it's related with cohomology theory. Plus beta x y. I think it is even here. It can be interpreted as a rational function of such type form, and it is seen that if you have special choice of psi and beta, it is corresponds to case when uij square equal to 0, this is cohomology, when uij square is equal beta y ij, it is K-theory, and this is cases of degenerate Hickey algebra, and if uij square satisfy quadratic Hickey relation, This is part of so-called Hessenbruch homology theory, which corresponds to rational function. This is really unique cases when up to isomorphism of all groups, when they satisfy associative Young-Baxter equation. Because associative Young-Baxter equation plays the central role. Okay. And if you have an elliptic case, you have additional quasi-constant which have relations, exchange relation with generators uij psi jk is equal to psi ik uij. This is, I call the quasi-constant. Maybe that's it. So in some sense, cohomology, quantum, cohomology, elliptic cohomology contains two sets of quantum deformation. Well, now I will skip. I just write some relation. I will write some relations. Yes, what I want to say now, questions. So this is a crossroad really of this theory. What is uij squared? In our case, it is beta uij plus psi ij plus qij. This is a Hickey condition. This is examples of the this is the works only in cohomology and K-theory. In elliptic case, which I want to now discuss, really I don't know any examples when beta not equal to 0, when you have no beta, and that's all. And another again problem to consider unitary case, because I say definition non-unitary case because it has many applications for trigonometric case and for graph theory and so on. One important thing of this algebra, commutative, if I consider commutative quotient of this algebra, it gives you deformation of so-called Orlik-Tarau algebra. This is a very important algebra in the theory of arrangement, plane arrangement. Yes. Now I want to consider elliptic case. And again, I want to quantize uij. We know what uij elements satisfy these two associative relations. And there is really one interesting thing, but in fact, if I consider so-called quasi-symmetric elementary polynomials, that means I have ordered sum of product of elements. In this, to prove that you have integral of motion, it is enough to consider only one relation, only one associative relations. But in this case, non-collaborated doesn't compute. But nevertheless, you have some quasi-integrable systems with non-commutative Dunkel elements. This is rather interesting. Yes, and now next step, construct commutative family of elements. Oh, sorry. Okay, so this and these relations are really extremely surprising. Even, and in some sense, basic case for this story is case cohomology theory, where all additional when we have degeneracy algebra, so, two degeneracy algebra, when uij square equal to 0 and uij plus, and it is unitary theory. Because in this case, it is easy to see that this algebra is the so-called braided Hopf algebra. And it is a so-called Nichols algebra, which means it is simple. And that is all the problem in theory, in the algebra, to classify the braided Nichols algebra. And the answer, okay, maybe I use this one. So you have relations, associative Young-Baxter relations, and you have 1-2 relations, and you have relations uij square equal to 0. Question, you have relations, quadratic algebra, important because the generator is equal to 0, and question, is it finite dimensional or not? And it is a very difficult problem, because and it really gives you some advance with various extension of Schubert calculus for more wide class of algebras. Anyway, it is not difficult to compute, to consider algebra. Okay, I commonly denote this algebra three-term relations. Yes, even in general there are 4-term relations, 3-term relations. Yes, and if n equals 3, then it is the algebra 3T. 3 is finite dimensional, and the dimension 12. If 3T4 is a surprising relation 24 square. If 3T5, it is even more surprising. But it is 4 square, 5, 6 square, and always square. And it is time to say that really I look on this algebra, on these relations, and relation for defining relation for real algebras and so on, as a relation for graph. If you have graph, in this case, complete graph. In this case, you can put generators for any age and put loop in any vertex and define in similar way defining relation for graph. And of course, very surprising, and 3T6, it is a problem. Because this is in some sense very simple algebra. It has 15 generators and 100 relations. Why it is finite? Conjecture is infinite dimension, and really it suggests general conjecture for Golod-Shafarevich type, for finite dimensionality of important quadratic algebra. Okay, again, very important things to understand what is the basis of this algebra. Yes, and this square really has a simple interpretation, because this algebra contains a triangle. 1, 2. Okay, I to simplify notation. 1, 2 means U12. It generates 1, 2, 2, 3, blah, 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 n minus 1, n. This is A very important case of this algebra with algebra generated by simple generators corresponds in this case either Coxeter, Neal-Coxeter algebra, either it's degenerate algebra, yes, and in general it corresponds to Hecke algebra. But if I will start, it's also quantum Hecke algebra. This approach suggests what is quantum Hecke algebra. Okay, what I want to say. Okay, yes, really this squares is very simple, not simple, but it has a clever explanation which is really not clear for 6. So this is a very, okay, this is an old problem, but no way to, at least now, no way to. Okay, now I want to come to elliptic case. As you see, you don't have Young-Baxter relations. Okay, you don't have Young-Baxter relations because difference between left part and right part of Young-Baxter expression, it is not zero. It is just depends on these quantum corrections and on the psi. And it is a natural question that can we quantize this classical Young-Baxter equation. And again, here surprising things that in general, if you have a classical Young-Baxter equation, it is some trouble to quantize, to find analog of quantum Young-Baxter equation such that natural limit of this quantum Young-Baxter relations gives you classical Young-Baxter equation. But in this case, you can, it is general case really, if you have a solution to classical Young-Baxter equation and plus locality condition, then you write what is a quantization of this classical Young-Baxter equation, and it is define Rij. It is psi ij. This is later I will specify, I just construct a representation of this algebra, and it is clear that the representation is well known, and so on. But there is another representation which is less known, but that's less useful. Okay, Rij. And the theorem that Rij really satisfies real, honest Young-Baxter relations. And proof really not so easy, but nevertheless direct. And it uses this assumption that element Uij satisfies classical Young-Baxter equation. And in some sense it is easy to understand that what is written here, it is a commutator between classical Young-Baxter relation and the sum of generators. If you, it should be zero because you have classical Young-Baxter relation. And here you have to suppose, you have to suppose your psi, your dynamical parameters, psi square is psi square bar. Square square bar is equal to psi square plus q. And it is later I will give realization of this. And this is it. So Rij really solution. But now maybe I need to write the representation. This is very interesting, very nice problem, yes. But I don't want to order some price for solution of this problem because I'm not sure it's possible to solve in the short time. Anyway, what is the representation of this theory? I skip, of course, trigonometric and rational cases because it is rational, it is a Colangelo type models, and here relation Eli-J, really well-known area object. This is what I call the Kronecker sigma functions. And this function really appears in many talks. So it can be right in terms of theta functions, but theta functions satisfy relation degree 4. But I want to have relation degree 2. So I can write it in terms of Kronecker sigma functions. Sigma. You have dynamical parameters lambda I, lambda j, and you have xi minus xj divided by sigma lambda I minus, sigma lambda I minus lambda j xi sigma lambda I lambda j y. And you commonly in order in computation you have to put here some constant, but I skip constants because it is not important for quadratic relations.
But
this is Kronecker
y should be xj or?
Sorry?
Your y should be minus xj or?
Why no? Sorry, xj. But maybe I mistake. But anyway, this is Kronecker sigma function, which you can read from the book of Whittaker and Watson, page number 451. So this is Kronecker sigma function. It satisfies. You can rewrite Riemann relations for freedom relation degree 4 and the freedom relations degree 2 for Kronecker sigma function. But it does not define, it does not satisfy the associative Young-Boxer equation. In order to do this, you have put here what I call operators K-I-J. This is exchange operators. This is a relation where the relation over in the symmetric group. This is a elliptic representation. Of course, this is and again the classification solution of the classical Young-Boxer or the associative Young-Boxer equation, which have enough number of derivatives, was done by Hermite maybe almost 150 years ago. So it's well known, it's written in book with Kirillov, and it is a very remarkable book because it contains a lot of information from sigma and p function, Weierstrass p functions. Wow. Okay, just look on book with Kirillov, it's a very nice book. Yes, and this is satisfied. And of course, this is not general solution because here you can use so-called theta function, sigma function with parameters. It means you have to multiply by some power y over x. Okay, I use this one. Yes, and remarkable observation which was done Uyeda and Chibukova, and it is based, this element really is operator form of very famous Delaunay and Greenfield elliptic connectors. this one, but Lij, Lj, which is psi ij minus, okay, some parameter here, uij, if it is introduce certain coordinates and something, you can prove it matrix element of these operators, you can give the new related with Galois-driven R matrix. Yes, and proof I will write. Why I want to sorry. I have to finish. No, I have probably 20 minutes. No.
Minus 5.
Sorry?
No,
Minus?
minus.
Okay, sorry. I just stop on the Russian models and so on. Remain, why I just try to construct solutions, because there is a very famous paper by C.N. Young, who really proved that if you have solutions to the Young-Baxter equation, I call it constant solution to the Young-Baxter equation, but you can imagine that really there is some parameters here. But I skip it because it depends on these parameters, it's just ij. So I can, commonly it is xi minus fj, but it's not important. You just write, okay, and one thinks that you can standard way, really this is ordered, if you wish, additive Dunkel elements is some of some generators, which is really definition, various definition. This is what is the Chern form, not Chern classes, but Chern form. For it involves some relation structure and so on, and global this is, and roughly speaking, this is a trace of this matrix. And this is the meaning of QIJ. Yes. And it is easy to construct with additive, multiplicative Dunkel operators. This is also very important. And this can be looked for as an ordered product R matrix. This is, you know what is theta big? Theta pi is a product of R J I, okay, J A, which is product at A equal to I minus 1 to 1. I skip some place. And a similar product of A from I plus 1 till N R G R G R E I. Where appears localization. This is rather important in the story. Where localization appears that here in interface this is really, I R minus 1. And if you, from this quadratic relation, it follows that it is Lij, and this is really Li divided by some rational function. And you have to add this rational function in order to derive this relation from the standard. Yes. And important things, where elliptic. Really, if you have a family of Li, some elements which is a representation of your R matrix, that means Lij, Li, Lj is equal to Lj, Li, In this case, you can substitute this as AI. And this element still commute. And AI here maybe, and important property here, important solutions to this relation is just AI is equal to just 1. Li is multiplication by xi, Li is differentiation di, and Li is shift operators in xi. And if you substitute here xi q, this is exactly Ruiz-Henar's function. And I close with my talk before. Let us forget about this. Let us assume that we substitute only 1. Because in this case, you can compute explicitly relation between elliptic Dunkel elements, and this relation, my conjecture that it is exactly quantum cohomology of Flock varieties. A bit deformation, which I don't have time. Okay, you can construct certain determinant that are generating with relation in the quantum cohomology of cotangent bundle also can be written in terms of explicit formula, which is a reformulation formula, known formula by recent paper, Mihalcea, Su, and someone, I forgot, Lee, but it has a very complicated first name. And also, but it comes really, again, rewriting of formula written by, okay, I will say Mushin, Tarasov, Marchenko, long before the result of Su and company. Okay, I will stop, because it is story for infinity.
Thank you very much.
Okay, I didn't say very important things. How it's related with Schubert calculus, how it's related with classes. Because there is another representation which is not physical meaning. This is called the Brion representation. And it relates with algebra, with cohomology of Flock varieties, and so on. There is another representation. This algebra is this representation, Brion representation, which relate this story with algebra and, for example, with relation between elliptic Dunkel elements.
So, you have some questions or comments?
So in elliptic case, you have psi ij is also given by sigma.
Sorry? I hear very nice.
In elliptic case, you have psi ij is also given by Kronecker sigma. Where the role of lambda and x exchange.
Yes, phi j is a P function, Weierstrass P function.
Huh?
Yes, but this is for standard representation corresponding to Milan-Briggs.
No. I'd like to know that in the elliptic case, what is psi ij?
This is quantum corrections.
Yeah, so it's given by
with quantum corrections. Yeah, and because the number of quantum corrections bigger than number of quantum parameters, I don't know. Interpretation is the following, because it is well known that cohomology theories, quantum cohomology of Flock varieties, or Grassmannian, related to so-called Toda lattice. integral of motion for total lattice. But I consider really what is called a full constant to the lattice, which is the generalization of total lattice. And in some sense, this is a degeneration of integral of motion for full constant to the lattice, which is really well known and written in some details. So this is the generalization of these things for full constant to the lattice.
I think if your psi ij is given by a Kronecker sigma where the rho of lambda and x are exchanged, then your Rij is almost the same as Nomi-san obtained.
Sorry,
Okay, let's discuss it later.
Huh?
Let's do it. Your Rij is given by psi ij minus Uij.
Это не фай, это psi.
And you gave us Uij is given by Kronecker sigma times exchange operator.
It is a Kronecker sigma function.
Right. And I was wondering, psi ij is also given by a Kronecker sigma.
Okay, I think it's better to discuss.
If so, that is your Rij is almost same as Nomi-san obtained. Or it's known as なんだっけ、上の渋川 R.
Okay, sorry, I don't understand. We will discuss.
Okay. So, any other questions?
Maybe it will be split, but maybe I wrote psi as phi. It's possible.
Or you call it
You think this relation is a relation of this is generalization of Hecke algebra. It is quasi-finite Hecke algebra. Because commonly in Hecke algebra you don't have, you have just, and parameter in Hecke algebra is quantum parameters. It is very Yiddish, but it comes from quantum group, from quantum cosmology.
So, any other questions or comments? If not, let's sound speaker again.
Okay, I don't understand what. Okay.
You don't know the Ueno Shibukawa R. I was wondering this I think square of this is not the deformation, but just one or square unitary. I want to say that you can also obtain R by using visual satisfying the dynamical
This is for why it is over here. My point is, I want to relation. And this is really much easier way to prove.
Do you know the general solution of energy you think these are?
I don't know how I would solution. Because basically in this case, which is a quantum case. Because in this case, it gives you elliptic. You can normalize here and Lij equals to 1. Lij Rgi equals to 1. This is a representation of elliptic rotation of symmetry. So I don't know elliptic rotations. So we have finished. Okay. Do you have some comments?
No, but yeah, I mean.
But formally you use only relations, not basically one of the main properties of elliptic function, but it is double periodic.
So it may be possible that the linear computation
Yeah,
I see. So only those, I mean, we will have something like this. Sorry, times it's not possible.
I know what you have.
This also satisfies.
Yes.
That's the weather.
Yes.
Now it's okay.